about Atle. Our first speaker is Kannan Soundararajan, who will talk about Selberg's contributions to the theory of the Riemann Zeta function and Dirichlet L functions.
Thank you very much. It's a great honor to be asked to speak at this memorial meeting. Selberg was a great source of inspiration to me, and I think I was quite intimidated by him when I was here, and I did overlap with him, which I regret a bit now, but at least I did get summon up the courage once to ask him to autograph my copy of his collected works, and I'm very glad I did, and that's a prized possession that I have. So today I'll tell you something about his contributions to the zeta function and L functions. The title is actually the title of some of his papers. So let me begin by recalling what the Riemann Zeta function is. So we have a Dirichlet series 1 over n to the f, which can also be written as a product over primes. The product over primes is simply the statement that you have the unique factorization of numbers into prime numbers. And both the series and the product converge absolutely when the real part of S, which is usually written as sigma plus it, is bigger than 1. And Riemann showed that this function extends meromorphically to the complex plane. It has one simple pole at 1, and that pole has residue 1. Sorry? Can you tell me when it gets better? Is it better? No? There? Yes? Okay. And there's a functional equation which was proved by Riemann which connects the values of the zeta function at S to the values at 1 minus S. And this just involves some power of pi and the Euler gamma function, like so. And since the gamma function has poles at 0, minus 1, minus 2, etc., one can see that there must be some trivial zeros of the Riemann zeta function at minus 2, minus 4, etc. The non-trivial zeros are denoted by rho, which is beta plus I gamma. And the fundamental problem in number theory is to understand the location of these zeros. So from the Euler product and the functional equation, from the Euler product, one can see that there are no zeros to the right of 1. And from the functional equation, it follows that there are no zeros to the left of 0. And that's more or less what we know. So there's a beautiful result of Hadamard and Delavalle-Poussin. This is the proof of the prime number theorem, which makes the modest saving that in the less than equal to, you can drop the equality. So the zeros lie strictly between 0 and 1. And the most outstanding open problem in number theory, and maybe also one of the most outstanding problems in mathematics, is the Riemann hypothesis, which says that all the non-trivial zeros of the zeta function lie on the line, the real part of S equals half. So much of what I'll discuss about Selberg's work revolves around this. So I should first orient you by telling you how many zeros of zeta there are. So you can count very easily the number of zeros with ordinate lying between 0 and t. Now, there are some symmetries of the zeta function. The functional equation tells you that the zeros are located symmetrically around the critical line, real part of S is half. And by complex conjugation, they're also symmetrically located around the real axis. So we can restrict ourselves just to the case where the ordinates are positive throughout. And the simple application of the argument principle allows you to count how many zeros there are. And the shape of this answer really comes from the functional equation here, the gamma function is one whose argument grows like t over 2 pi log t over 2 pi, and that's what we see as the main term for the number of zeros. And there's a quantity s of t, which will play a major role later in this talk, which is the argument of the zeta function at t. So you define the argument by taking the argument to be 0 on the real axis, like at a point 2, say, and then you continuously vary the argument until you get to 2 plus it, and then you see what happens to the argument as you vary continuously from 2 plus it to half plus it. Now, the first great results of Selberg on the zeta function go back to a paper that he wrote in 1942. It appears as number 9 of his collected papers. This paper is introduces a lot of new ideas. He proves the amazing theorem that you can actually get a positive proportion of the zeros of the Riemann Zeta function lying on the line real part of s equals 1/2. The Riemann hypothesis tells you that all the zeros must lie on this line, but Selberg is able to find some proportion of them which lie on the line. And the second result that he proves is that he can locate almost all of the zeros in the sense of density, almost 100% of the zeros, within a very small neighborhood of the critical line. So I'll try to explain both of these results now. So suppose we denote by n0 of t the zeros of zeta which lie on the critical line, which conjecturally should just be n of t. The first result in this direction was by Hardy in 1914, that you can actually find infinitely many zeros which lie on this line. And subsequently, Hardy and Littlewood improved this to getting n of t, at least t zeros up to t, which lie on the line. And you're off by this factor of log t. And this proved to be quite an interesting sticking point. I mean, there were many, many proofs of the Hardy-Littlewood result by Landau, Siegel, Polya, Fekete, and others, but there was no real breakthrough over the t. So Selberg's result was the first time when somebody had gotten over t zeros. And in fact, first he proved that you could get t times log t zeros, which lie on the critical line, and then he was able to sharpen that soon afterwards to get t log t. In fact, due to some publication delays, his worst result actually appeared later in print than the better result of t log t. So how do we place these zeros on the line? So if you take a point on the critical line, and you take theta of t to be the argument of this factor which appears in the functional equation, then if you define z of t to be e to the I theta t times zeta half plus it, then what you see is that this is basically the same quantity as what happens in the functional equation, except for the magnitude of the pi to the minus s over 2, gamma of s over 2 has been taken out. So therefore, the functional equation tells you that there's a symmetry that z of t is the same as z of minus t. But if you conjugate both sides, you also see that z of t is the complex conjugate of z of minus t. So therefore, you conclude that z of t must be a real number. So in other words, we actually know what the argument of the zeta function on the critical line is, except for the sign, plus or minus. And then the idea is, now you have a real valued function whose zeros you want to understand. And this we can hope to do by just counting sign changes in z of t, and every time we have a sign change, we know that we have located a zero which is on the critical line. So for example, Hardy starts by looking at the integral from t to 2t of z of t and compares it with the integral of the absolute value of z of t. If there's no sign change, then both integrals must be the same. But on the other hand, you can show that the first integral is little o of t, so there's a lot of cancellation in z of t. the second integral one can show is at least as large as t. And so therefore, between t and 2t, you can get at least one zero of the Riemann Zeta function lying on the critical line, and so there must be infinitely many such zeros. Now, if you want to get more zeros this way, then it's clear that what you have to do is not to have a long interval such as from t to 2t, but you need to be able to count sign changes in very short intervals. Now, this argument can be modified and was modified by Hardy and Littlewood to have, if you have intervals around t of length some power of t, then you can still show that there must be a sign change in every such interval. But when you have a very short interval, which is smaller than a fixed power of t, that fails. It need not be true that well, you cannot prove that every such interval does contain a zero. So instead, what Hardy and Littlewood did was that they looked at an interval from t to t plus a, where a is some large constant, and instead of asking that every such interval contains a zero of the zeta function, they only wanted to know that for a lot of values of t, you can find a zero in such an interval. And here's how you can do that. So you do this by basically taking an L2 estimate. So if you look at this variation of the integral from t to t plus a of zeta of half plus iy, usually we expect it to be of size a. And they're able to show that on mean square, that integral is small, this integral, which tells you that usually, if you take the integral of the absolute value of the z function, then you get that it's usually of size at least a over 2. But on the other hand, you can take an L2 estimate of the integral of z of t without the absolute value, and then you can show that that L2 estimate is very small. So it's of size a times t. And what that means is that usually the integral without the absolute value is only of size square root of a. And therefore, you get that, let's say you can make this happen 99% of the time, that you get the integral of the absolute value being as large as a over 2, and 99% of the time you can make this smaller than a over 2. And so at least 98% of the time, you will have a zero in the interval from t to t plus a. Now the problem is that the Riemann Zeta function has about t log t instead of t zeros. So if you want to prove Selberg's positive proportion result, you need to consider even smaller intervals than intervals of constant length. So you need to consider intervals of length about a constant over log t. So, and if you can get many such intervals containing a zero, then you would get t log t zeros as needed. And this is not possible to do by the Hardy-Littlewood method. And the reason for it is, well, you can do both estimates. You can take the mean square of the integral of z without the absolute value, and you prove a result similar to what I have here, similar to this result. And all that it tells you is that usually the integral without the absolute value is of size square root of a over log t. But on the other hand, you can show that typically, even if you put the absolute value, it is in fact not of this size. It is much smaller. And the reason for this phenomenon is roughly that if you take the integral of the second moment of zeta, then that's of size about t log t, but the first moment is not of size t log t to the 1/2. It's much smaller. It's of size only t log t to the 1/4. So in other words, what we see here is that the values of zeta are quite wildly varying. The first moment captures some of the behavior, but the second moment amplifies the larger values of zeta. And so since zeta doesn't have a uniform size, there is some loss when you try to estimate things using the second moment and the first moment. And this was a crucial idea which was introduced by Selberg to circumvent this. he uses something which he calls a damping factor. So actually, I don't think he calls this a damping factor anywhere in print that I've been able to find, but I think in conversations he somehow seems to prefer this term to describe something which we now usually call a modifier. And the idea of a damping factor is it's a quantity which is always going to be non-negative and which will have the property that when you multiply it by zeta of half plus it, you get a function which is usually of constant size, so that it will neutralize this discrepancy between the first and second moments that you see. And here's how he constructs such a damping factor. So you take this eta of t, which is given in terms of the coefficients of 1 over square root of zeta of s. So it's something that we can write down in terms of binomial coefficients. And the idea is to take a truncation of this series defining 1 over square root of zeta of s and hope that this truncation is usually going to be close to 1 over square root of zeta s. So in other words, when you take zeta of half plus it and multiply it by the absolute value of eta of t squared, our hope is that it'll still have some fluctuations in sign, but maybe the size of it is almost always constant. Okay. So now we can study the sign changes of z of t times eta of t squared. And this is the main result that Selberg proves. So he gets estimates for the L2 norms of both the integral over an interval from t to t plus a constant over log t without the absolute value sign, like here. And also proves that when you take this exactly as in the Hardy-Littlewood method. So for the integral with the absolute value sign, using this L2 estimate, you can usually say 99% of the time, you can get that absolute value is at least of size the length of the interval. And so now you have the result that you need. So most of the time, if you choose a large enough value of A, you can conclude that there will be, say, for 98% of the values t, you can find a 0 between t and t plus a over log t. And this, of course, proves that there is a positive proportion of zeros which lies on the line. And Selberg actually proved a little bit more. You can actually guess from this 98% that I wrote down that if you take larger and larger values of a, if you allow your interval to have slightly longer length, then almost all such intervals t will have at least one zero of the Riemann Zeta function. So Selberg never really computed what proportion that he gets. And this was computed in an Oxford thesis by Min, who I think was a student of Titchmarsh. And it turns out that the proportion that you get from this is extremely small. This is one of the famous jokes of Selberg, that he liked to say that if a student named Max had computed the answer, then perhaps the answer would have been larger. So this is one of the main results in his 1942 paper. And the other result has to do with putting many zeros close to the critical line. So here the idea is to count zeros n sigma of t, where I'm interested in the real part of a zero being larger than sigma. Of course, we don't expect these zeros to exist because we expect all the zeros to lie on the critical line. So we are really, in some sense, studying the empty set, but of course we can't prove that it's empty here. So what we aim to do is to show that this set n sigma of t is at least not very big. There's a lot of people before Selberg who had worked on this. So Bohr and Landau were the first to study this, and Carlson and Ingham. And Ingham produced a very beautiful result on this, which says that if you're to the right of half, say at least half plus delta away, then you can get a saving in the power of t of how many zeros that you have which violate the Riemann hypothesis. And then in many situations, Ingham's result still has not been improved. So it's quite a striking result. And what it proves is that you can you can get almost all the zeros of the Riemann Zeta function to lie within a distance of log t over log t, something which goes to 0 from the critical line. Now, Selberg makes an improvement to this, which is that he's able to narrow down this region and say that you can localize most of the zeros of the Riemann Zeta function to be within essentially a constant over log t from the critical line. This looks like a little bit technical, but actually it turns out to be a really fundamental result. There's a density result that he proves, which is more precise in this context, which I'll mention, which turns out to be extremely useful and can substitute for the Riemann hypothesis in many cases. But also what I want to indicate here is a method that he uses to produce this result, which is again related to this idea of finding a damping factor. So here the idea is to find these numbers lambda n are arbitrary real numbers. And let's just normalize it by setting lambda 1 to be 1. And the idea is to minimize this integral of zeta of half plus delta plus it times this damping factor and its difference from 1. Suppose you could do this and prove that this quantity was always small, then what that's telling you is that zeta times psi is usually about size 1. And if zeta times something is usually about size 1, then that means that zeta cannot be 0. So that tells you that can be used to give these zero density results. Now, what Selberg notes is that if z is a small power of t, let's say t to the 1 over 20 or something like that, then you can evaluate this integral accurately. And let's say if you just look at the case where delta is 0, the shape of the answer that you get has the shape of being a quadratic form in the lambdas, because after all, it's a mean square which is being evaluated. And then we have a simple problem, which is you're given a linear form which is fixed. The first coefficient, lambda 1 equals 1, is fixed. And then you have a quadratic form in the lambdas which has to be minimized. And Selberg figures out how to solve this optimization problem by just diagonalizing the quadratic form that you have. And you can do this. And he finds that the choice of lambda n's is something like, is the Möbius function, which is not very surprising because if you have the sum of mu n over n to the s, that's roughly 1 over zeta of s. So it's some truncation to 1 over zeta of s, which this damping factor psi is, times some kernel log z over n over log z, which is also optimal. And this simple idea of trying to optimize this quadratic form actually turns out to be very powerful. And this idea is closely related to the idea of Selberg sieve, which John will talk about next. So these are the two main theorems in his 42 paper. And I can tell you some of the developments that came out of this. So in 46, Selberg proved analogs of these results for Dirichlet L functions. So you can, certainly if you just fix a Dirichlet L function, you can prove that a positive proportion of its zeros lie on the critical line. But he also proved more interesting analogs, like if you take a small interval near the real axis, say from 0 to a over log q, then he proves that if a is sufficiently large, then you can find many, many characters chi mod q having at least 1 0 in this interval, which lies on the critical line. Then in the 80s, Hafner adapted Selberg's method to prove that a positive proportion of zeros of modular form L functions also lie on the critical line. In the 70s, by a very different method, Levinson managed to put a very large number of zeros on the critical line. He managed to put a third of the zeros on the critical line. So the initial starting point of Levinson is different, but eventually you still use this idea of having a damping factor, which Levinson called a modifier. And I think this term somehow seems to have been inspired, and it's a term which is still which is more popularly used now. But one interesting consequence of Levinson's method, which was observed by Selberg and independently by Heath Brown, is that Levinson's method actually produces simple zeros of the Riemann Zeta function on the line, whereas Selberg's method only produces odd order zeros. You can show, but you don't know that the zeros have multiplicity 1. Exactly. But the two methods are quite different in spirit. For Selberg's method to succeed, this damping factor can have any size, whatever, and you don't need to make a calculation. The answer that you get might be bad, but in terms of the constant that you produce, but you will always produce a constant. In Levinson's method, you can, when it works, you can produce a big constant, but sometimes it just doesn't work. For example, it doesn't work for modular formal functions, as in the result of Hafner. So these ideas of using modifiers or damping factors are very central to recent work which has been carried out on finding zeros or vanishing or non-vanishing of L functions at the central point, let's say at half. So there's many people who worked on this, some of whom I've mentioned here. Now, the second result that I mentioned of Selberg in this 42 paper was this zero density result, putting many, many zeros within a constant over log t of the critical line. And a stronger version of this was given by him in 46, which takes this shape that if you're delta away from half, then the number of zeros that you have is a factor t to the minus delta over 4 better than the trivial estimate of t log t. So you can see that if delta is a little bit larger than 1 over log t, then you're producing a lot of, your estimate is a tiny fraction of the total number of zeros that we have. And again, an analogous result of this type was proved by Luo for modular formal functions. And while I'm still on the subject of zeros, I'll tell you this lemma of Selberg, which seems a little difficult to parse, I think. So the point is you have an analytic function, and if you're counting a big box, then there's a very simple application of the argument principle that you can use to count how many zeros that you have in a big box. However, if you have a tiny window in which you want to count the zeros of an L function or just any analytic function, then what you might want to do is to find the change of the argument as you vary over your box. But the problem is the horizontal line segments may be of almost the same length as your vertical line segment. And you don't want to face ever the imaginary part of the logarithm, because the imaginary part of the logarithm already encodes information about the zeros, and you want to avoid the imaginary part of the logarithm. The real part of the logarithm is friendlier because that's just related to the size of the function, which you can hope to estimate by some methods. So what you would like is a version of the argument principle where you can count the number of zeros in a box in terms of just the real part of the logarithm of a function. And that's what's provided by this lemma. You have this complicated function, which all we really care about is that it's positive. It's counting at least all the zeros in your box with some weight. And on the right side, you have an expression for it which is given in terms of the logarithm of the function, but you see you only have the logarithm of the absolute value of the function up here. So this is not a very difficult exercise in complex analysis. It's closely related to the idea behind the Fragment-Lindelof principle. But it turns out to be an extremely useful lemma. And in recent years, it's been used by Kowalski and Michel, and also by Michel and Heath Brown in problems involving low-lying zeros of L functions. And a few years back, Conry and I used it to prove that there are many quadratic Dirichlet L functions with no non-trivial real zeros. And this really crucially depends upon Selberg's lemma and also these ideas behind the modifier. Now, that's the story about Selberg's work in this 42 paper. Now I want to tell you something about a few papers that he wrote in 1946, 3 papers which have to deal with certain statistics involving the Riemann Zeta function. So I want to tell you his motivation behind these papers, which is still concerned with the Riemann hypothesis and the problem of putting zeros on the critical line. So once you have a positive proportion of zeros on the critical line, you could say that the next step forward would be to continue this to show that at least 100% of the zeros could be put on the critical line. But Selberg is pessimistic about this, and he says that this is unlikely to be proved by these methods because this would demand a much more regular spacing of the zeros of the zeta function than is really the case. So I want to explain why he says this and what it led him to, which is, in my opinion, as interesting as any of these results on putting a positive proportion on the line. So recall this function theta of t, which we used to create a real valued function on the half line. And by Stirling's formula, you can work out an asymptotic for this. It's about size t over 2 times log t. So there are some special points of this function called gram points, where it takes a value which is an integer multiple of pi. So that if you have e to the I theta t, then you get either +1 or -1. So these gram points are, of course, very evenly spaced. It's very easy to work out an asymptotic for them. Now, at the gram points, our function z of t is just plus or minus zeta of half plus it nu. And there's a formula that you can write down for zeta of half plus it, which is called the Riemann-Siegel formula. There are many ways in which you can do something like this. But the crucial thing is to note that it starts with a 1, and then it has various signs, various terms which are oscillating in sign. So we can imagine that the terms which are oscillating in sign are more or less canceling out, and let's pretend that they don't exist. If they don't exist, then we have that zeta of half plus it nu usually looks like 1. And let's say, maybe even if it's not close to 1, we might expect that it's usually positive, let's say. If that's the case, then we would have, for 2 consecutive gram points, that the z function would be positive at one and negative at the other. And therefore, there would be a 0 of the Riemann zeta function between these 2 consecutive gram points. If this picture were to hold, then you would get the right number of zeros of the Riemann zeta function lying on the critical line, and you would basically be able to prove the Riemann hypothesis. And it seems to be true, at least initially. So I think the zeros up to 100, there is exactly a 0 between every 2 gram points. And Titchmarsh had done some computations on this, and he found that it's usually true even if you go up to 1,000. So this was in the days before a computer, so I guess 1,000 was still some fair degree of computation. It fails, there are about 1,000 cases, and it fails about 40 times. But what Selberg realizes is that there are actually substantial differences in the substantial irregularities in the distribution of the zeros of zeta. And what he proves is that the nth zero of zeta, if you look at the ordinate of the nth zero, which is gamma n, it never lies in the nth gram interval from Tn to Tn plus 1. So in other words, if you try to prove the Riemann hypothesis by trying to find a sign change in a very regular way, you're never going to be able to succeed. And what he also proved was that if you look at the consecutive spacings between the 2 consecutive ordinates, gamma n plus 1 and gamma n, there are t log t zeros up to height t, so the zeros are getting closer and closer to each other. So you multiply them by log gamma n, which is about a log t, to make sure that the spacings are usually of size 1. And then what he proves is that some of the time, the nearby spacing is a little bit larger than 1, and some of the time it's a little bit smaller than 1. So they can't be regularly spaced like an arithmetic progression. And this is, of course, part of the reason why he believes that you will not get 100% this way, because if you take a short interval from t to t plus a constant over log t, it could happen from time to time that there would be 2 zeros which lie in that interval, and you would have only counted that as one sign change by the method that he uses. And so you will certainly miss quite a few zeros this way. So how does he prove this result? So I started out with this formula for the number of zeros up to height t, which has some main term and has this remainder term, which is s of t, which is the argument of the zeta function at height t. This argument usually doesn't get very big. It's only of size about log t. And if you assume the Riemann hypothesis, you can make a modest saving over it, a log t over log t. And it was known due to Titchmarsh that this argument can fluctuate. It can go off to infinity, and it can also go off to minus infinity. But Selberg proves this remarkable result that if you look at the distribution of the argument, so it's pi times s of t, then the distribution is approximately Gaussian with mean 0 and variance half log t. So what this means is that because this variance is usually very large, usually this quantity s of t is something which is fairly large. It's of size square root of log t, usually. And that means that usually, if you look at the nth zero, it's going to be some distance away from the nth gram point on a scale of square root of log t from the nth gram point. So you're never going to get gamma n in this interval tn to tn plus 1. And the way he proves this is that he computes the moments of s of t, on which you can see that this main term that arises here, these are the coefficients of the Gaussian moments. And so since the Gaussian distribution is determined by its moments, you can conclude this result. This paper is really, so this is carried out in 2 papers in 1946. The first one proves this result conditionally assuming RH, and then he has to work very hard to remove RH and prove this unconditionally. And it's here that the zero density result that I mentioned of his comes in very useful. It allows him to completely circumvent RH in this proof. Here's the briefest idea of the proof. So if you just look at the logarithm of zeta half plus it, you have a sum over primes of the logarithm of 1 minus 1 over p to the it, p to the half plus it. You take a Taylor expansion for it. That series doesn't converge, but you can truncate it somewhere and hope that that still is approximating the imaginary part of the logarithm. So that's the truncated series here. And what Selberg is able to prove is that most of the time, this truncated series is actually a good approximation to s of t. This argument is quite remarkable. It's still a very difficult and hard to follow argument. I mean, every time I have to reconstruct it, eventually I have to go back to Selberg to figure out the right way to do it. The main idea is to express s of t in terms of primes and zeros of zeta, and then he does some magic by which he's able to transform the zeros back into primes, and then he's able to evaluate the contribution of the primes. And he also proved similar result for the real part of the logarithm, so which is just the size of zeta half plus it. And he proved again that this is also distributed like a Gaussian with the same mean 0 and the variance half log t. And moreover, the distributions of the imaginary part of the log and the real part of the log are independent. Statistically, there's no correlation between them. And this result is very beautiful and has led to work by many, many authors. I'll give you one version of this, one variant which is due to Fuji, which is that if you look at an interval from t to t plus h, where h is fairly small, less than 1, but h times log t goes off to infinity, then the number of zeros in that window has a Gaussian distribution with mean, which is the expected number of zeros, h over 2 pi log t over 2 pi, and variance, which is a logarithm of this h log t. So one thing that you can see here is that the variance is very small compared to the mean that we have. If you have distribution of random numbers thrown down, then the variance typically there would be roughly of size equal to the mean. Whereas here you see that the variance is of size only the logarithm of the mean. So this is a hint of an interesting phenomenon. And in general, in all of these works, Selberg seems to have come very close to asking a very basic question, which is, what is the distribution of spacings between zeros of the zeta function? So his result on the lim inf and the lim sup being removed from 1 is one consequence of understanding what this distribution would be. But the question seems to have been first asked by Montgomery, and it's this famous pair correlation conjecture of Montgomery, supported by experiments of Odlyzko. And what this has led to is the idea that the spacings between zeros of the zeta function correspond to spacings between consecutive eigenvalues of large random matrices. Let's say unitary matrices chosen with respect to Haar measure. Now, random matrix theory has proved to be very useful in understanding properties of the zeta function. So I want to tell you one example of that, which is the work of Keating and Snaith, which is actually which is influenced by Selberg's theorem on the Gaussian distribution of log zeta half plus IT. So Keating and Snaith started by noting that you have Selberg's theorem, which says that these objects are Gaussian. But even if you take a large value of t around size 10 to the 20, and if you compare the distribution of log zeta of half plus IT at that height to the Gaussian distribution that is the theorem, then the fit of the numerical data to the theory is not very good. This is kind of startling because you have conjectures on the spacing of the distribution of gamma n plus 1 minus gamma n, and the fit of the conjectures to numerical data is excellent. You don't see any difference between the theory and data, whereas you have a theorem here which has very poor fit with numerical data. And what they wanted to know was whether you can explain this deviation of Selberg's theorem from the numerical data by some systematic way. And they formulated a more refined model which says that if you're interested in properties of the zeta function near height t, then you should consider not large random matrices. In other words, you shouldn't let n go to infinity, but you should pick a particular value for n. And the value for n that you should pick should be that n should be of size about log t. And the reason is, if you have a unitary matrix of size n, then you have n eigenvalues constrained to lie between 0 and 2 pi. So the mean spacing is 2 pi over n. And if you're looking at zeros at height t, the spacing between two consecutive zeros is 2 pi over log t. And you should naturally set these two quantities equal to each other, and that tells you what n should be. And this was a very insightful observation, which led to a solution, well, at least a conjectural solution to a problem involving estimating moments of the Riemann zeta function on the critical line. So you want to get some asymptotic formulas for the 2kth moment of zeta. And we only know how to do this for k equals 1 and k equals 2, which are classical results of Hardy and Littlewood and Ingham. There was a folklore conjecture that the kth moment should be of size some constant times t log t to the k squared. We had some idea of what this constant should be, that it should factor nicely as a product of some geometric quantity gk, which is an integer, times some arithmetic quantity ak, which is easy to understand. But it was not clear how to guess what the constant gk should be. So we know that g1 is 1, g2 is 2, and Conry and Ghosh managed to conjecture that g3 is 42, and then it took a lot of work to conjecture that g4 is 24,024. It didn't seem clear how to extend these computations. But if you use this model of Keating and Snaith, then what you should look at is you can model the absolute value of zeta half plus IT by the characteristic polynomial of a random matrix, G, which is chosen. So you look at the determinant of I minus G, and you want to ask in random matrix theory, you would like to know what the average of the 2kth moment is as you when you pick a random g. Amazingly enough, when you try to evaluate this integral, you land up with an integral which was evaluated by Selberg and published in a journal for high school teachers, I think, in Norwegian. So I think Peter will say something about this tomorrow, about this integral. And then they managed to find a conjecture for what gk is. So in the course of this work, they were also led to conjecture an analog of Selberg's theorem on the Gaussian distribution in families of L functions. So I'll give you one particular case of their conjecture, is that if you look at quadratic Dirichlet L functions, so these are generalizations of the Legendre symbol, and if you look at the values of log of L half chi d, then there should be some analog of Selberg's theorem that these should be also look like Gaussians with a mean which is not 0 in this case. It's a little bit shifted, which is half log log x, and variance, which is about size log log x. We cannot quite prove this, but if you assume some small amount, something about the distribution of low-lying zeros of these L functions, then you could use Selberg's method to prove some Gaussian distribution of this type. So, but returning to these moments, you can get lower bounds of the right order of magnitude for the moment, which is an old result of Titchmarsh. And recently, I was able to prove that you can get an upper bound. If you assume the Riemann hypothesis, you can get an upper bound for the moments, which is only an epsilon away from the right answer. And the basic idea for this method, for this result, is also largely based on Selberg's theorem. The idea is that if you can understand the distribution of the large values of zeta, then of course you will be able to bound the 2kth moment of zeta. So you really need to understand the measure of the set on which log zeta half plus it is bigger than some quantity v, say. This is exactly the sort of thing which is covered by Selberg's theorem, but in the region when v is fairly small, like square root of log log t. But if you could prove a version of Selberg's theorem uniformly in a wide range, then you would be able to use that result and be able to understand everything you want to know about moments. And what I was able to do was to adapt Selberg's techniques to prove such a uniform result, at least a one-sided version of it, and that leads to these bounds on moments. So these 46 papers of Selberg's have had a lot of impact on the field, and I think they're still continuing to have a lot of impact on the field. Now, finally, I want to say something about later work of Selberg, his 89 Amalfi paper, which also introduced a lot of new ideas in the field, where he axiomatized properties which we expect of zeta functions, like the Euler product or the functional equation, and formulated several conjectures on this, that that the size of the Dirichlet series coefficients at primes should be independent for different L functions in this family. So this is what's called the Selberg class, and this has also inspired a lot of work by Conry Ghosh and the Murthys and Kaczorowski and Perelli. And there are lots of very interesting results which have been proved by Kaczorowski and Perelli. So one thing is that they have been able to characterize the elements of degree 1 in the Selberg class and find that they are only the Riemann Zeta function and Dirichlet L functions. And recently, it seems they've been able to prove that there are no elements in the Selberg class up to degree 2. And if we could understand what happens in degree 2, then that would be a very big step forward. In the Amalfi paper, Selberg also studies the value distribution of log f of s, as in log zeta of half plus it, for values of s on the critical line or very close to the critical line. And he shows that if you take two different L functions, f1 and f2, then the distribution of the logarithms are statistically independent for different L functions. He also makes a study of the A points. So instead of looking at the zeros of f of s, he looks at the points where f of s equals a for some non-zero value of a, and studies where these points, the distribution of these points. And lastly, makes a very interesting study of linear combinations of Euler products. So you take n different L functions, L1 to Ln, and you form, and let's say they all have some Dirichlet series and they all have some Euler product, and they all have a functional equation, and we have to assume that they all have the same functional equation. So for example, they could be L functions associated to the characters mod q for some fixed value of q. And if that's the case, then you could look at linear combinations of these NL functions, and it turns out, it's a beautiful paper of Bombieri and Hegel, that if you assume the Riemann hypothesis for all these L functions and some other natural conjectures on the spacings of their zeros, then you can prove that almost all the zeros of these linear combinations also lie on the critical line. And this is a little bit strange because you have a situation where you almost have a generalized Riemann hypothesis, but these linear combinations really have no business satisfying a Riemann hypothesis. And they, in fact, have a lot of zeros, not of positive proportion, but still a fair number of zeros which are not on the critical line. And one of the ideas which is introduced in these works is that the linear combinations of such L functions are usually dominated by a single L function. And the reason for it is you have these n L functions, and if you look at the logarithms of these, each one of these is a Gaussian with a large variance. So each one of these will have some large size, but pick the largest one of that, and that will be much larger than everything else. And in a small region around that point, that single L function is going to dominate the behavior of this linear combination. There's been a lot of work on finding zeros of these linear combinations by Warren and Karatsuba, Hegel, and Bombieri and Hegel. But the last word on the subject rightly goes to Selberg. And about 10 years back, he proved that if you take, for many of such linear combinations, when the degree is at most 2, he goes back to his first result on a positive proportion of zeros of the zeta function, and he's able to prove the same result in this case, that you can get a positive proportion of zeros unconditionally, which lie on the critical line. Which is quite an amazing feat. It combines all these ideas of both the Gaussian distribution, knowing that only one of these is going to dominate at any point of time, combined with this idea of the damping factor which he introduced previously. So unfortunately, this is still unpublished, and I hope that some version of it will be written up soon. Well, thank you very much.